Good morning, this is Dr. Heidelberg, and today's presentation will discuss kinematics analysis. We are in Module 4 and going over here to the reference material, we'll click on a PDF, and that's going to be the presentation that we will cover during this session. We will also have the PowerPoint presentation, which you will be referring to as part of your homework assignment. In our presentation, we will cover some definitions of kinematic variables. We'll talk a little about vector algebra, kinematics of a point on a rotating frame. We see the difference between forward and inverse kinematics. We'll take a look at analytical solution and graphical solution to the kinematic problems, and also some common kinematic motion profiles which are being used in robotic analysis. The example over here is showing the Boulton-Watt steam engine, and it's been invented in 1784. What we see here is a flywheel, and we see a crank with a connecting rod, which is connected to the flywheel. The crank is being actuated by a piston that is getting steam from a reservoir here and a heated element that injects the steam to the piston. The piston is rising, and it actually causing the flywheel to rotate. The flywheel has high inertia at the periphery, therefore it could overcome the dead center on a way up. We see over here that we have also a governor. As the velocity is increasing, the governor is controlling the valves to regulate the velocity of the piston going up and down. We see over here that there's also an element that is pumping the water from an underground reservoir into the pool, and there's another valve over here that releases some of the water into the steam area chamber. The diagram shows a 4-bar linkage. This is one link, another link, and another link, typical 4-bar linkage known in kinematics, and also a slider crank mechanism, which is very well known in kinematics. So this is a nice illustration which shows typical kinematic diagrams, which is needed not only for patents but also for kinematic analysis of robot systems. When we're talking about robotic analysis, we have to first define some variables. We have coordinate systems, X, Y, Z, which is a global coordinate system fixed in space. Also, we have UV, we'll define as a local coordinate system, which is fixed to a rotating body. And when we put the hat over the coordinate element, we refer to a unit vector. Positioning vector are defined as R, R1, R2, also angle between two vectors is defined as theta. And then velocities, we have omega is absolute angular velocity, r dot is a relative linear velocity within a rotating body, and when we say dr dt, then we mean absolute velocity of vector r. It could be designated as r, r1, or r2. And when we take the second derivative, we're talking about the acceleration. dr squared dt squared is the absolute acceleration of r. And we have also an angular acceleration, which is defined as alpha or the derivative of omega, which is omega dot. Also, R double dot is the relative linear acceleration of R2 within the rotating body. And then we have vector algebra notation, such as A cos B is the cross product of vector A and B. The absolute value of a vector, which is a measure of its magnitude, a determinant of a matrix with two bars, and a transformation matrix T12 transforming a vector from coordinate system 2 to coordinate system 1. So we'll be using this definition in upcoming discussion. The cross product is defined as a vector which, according to the right-hand rule, when we have a vector A which is crossed with B, then the cross product is in the direction perpendicular to both A and B, and it is advancing in the directing in direction as a right-hand screw. Such we move A towards B, a right-hand screw will advance in this direction. So if we have a vector A here along a U coordinate and B along a V coordinate, then A cross B will be in this direction, advancing in a right-hand screw direction, in direction of W, which is perpendicular to both U and V. When we figure out the numerical values of the components of the cross product, we see over here we have UVW coordinate system. We have AU, AV, and AW as the coordinate of the components of the vector A. So if we have another vector B not shown here and we want to cross them, we can find out the components of the cross product by taking the determinant of the values UV W hat. These are the unit vectors, and then we put the components of each vector A and then B, A cross B. You see A, U, A, V, A, W. These are these elements. Similarly for the B. And then when we take the determinant of that, we see that the U element is AV times BW minus AW times BV. Both will be sharing the component in the direction of U, and this will be the component of the cross product of A cross B. Similarly, we get the components in the V direction and the W direction for the cross product. When we expand that in determinant, we pretty much get the same results. When we're talking about vectors, both acceleration and velocity, it is important to be able to transform these vectors from one coordinate system to another. For example, Newton's second law, when we talk about dynamics, are expressed in the inertial coordinate system fixed to the ground, and the vectors may be defined in a moving coordinate system fixed to the robot link. So it is important to be able to transform vectors such as A, which is described in a rotating coordinate system, x2, y2. We want to resolve it into the coordinate system x1 and y1. And in order to do that, we have to develop the matrix of transformation. There are many ways to develop that. I like to memorize that such that if you are transforming from a rotating coordinate system to a fixed coordinate system, or it could be from one coordinate system which is rotating to another coordinate system, but the second coordinate system is rotated an angle theta, then the transformation matrix is simply constructed as following. We put on a diagonal cosine theta and cosine theta along the axis where we are defining the vector, such as x and y, and we put 1 along the diagonal of the axis which does not change. In this case is the z-axis. Z-axis is common for both x1 and x2 coordinate system. So we have cosine theta, and 1, and then we put 0, 0 on the column and the rows of the 1, and then we have left with the off-diagonal terms. So we put minus sine theta on the first row, and then on the cos element we put sine theta, and that construct the transformation matrix from coordinate system 2 to coordinate system 1. So if we have a vector with component ax2, ay2, az2 in coordinate system x2, y2, z2, and we multiply times the rotational matrix or transformation matrix from coordinate system 2 to 1, then by doing this multiplication, cosine theta times ax2 minus sine theta times ay2, and then we do the same for the second element, and the third element does not change, then we get the components of this vector resolved in coordinate system x1 and y1, z1. If we want to do the opposite, in other words, take a vector from x1, y1, z1 and transform it to x2, y2, z2, then the transformation matrix is basically the transpose, where we take the minus sign and we put that minus sign over here, and the plus sine theta, we'll place it over here, and we get the inverse transformation, which transforms from coordinate system 1 to coordinate system 2. We extensively use the Euler angles for the wrist of a robot with a yaw, pitch and roll, and the transformation matrix are defined pretty much the same way we showed it earlier. So we start by taking the coordinate system x1, y1, z1, and we provide a yaw with an angle theta, and we get x2, y2, and z2. So this is the first angle, and then we get the yaw. Once we get the coordinate system 2, we rotate on we rotate the pitch along x2, so x2 and x3 stay the same, and y3 is moving up, and z3 the same, and then finally we do the roll along the z3, which stays the same as z4, and then x3 and y3 are moving to become x4 and y4. The transformation from coordinate system 2 to 1, the same as we saw before, is cosine 1, cosine theta 1 and 1, and then minus sine theta 1, and then we have sine theta 1, same transformation as we saw before. From 3 to 2, we see that over here the x doesn't change, so we put the 1 over here with 2 zeros on a row and 2 zeros on a column, and then we have cosine theta 2, cosine theta 2 minus sine theta 2 and sine theta 2, and similarly for the roll. When we get the complete transformation from coordinate system 4 to coordinate system 1, you see that we can take the transformation from coordinate system 4 to 3, multiply that times the matrix transformation from coordinate system 3 to 2, multiply that times coordinate system 2 to 1, and the whole transformation becomes rather complex matrix, transformation matrix, and we take this matrix This is abbreviation of cosine theta 1, cosine theta 3, minus sine theta 1, cosine theta 2, sine theta 3, and so on and so forth. And we multiply times a vector which is represented in coordinate system 4, then the multiplication will result the same vector transformed to coordinate system 1. Let us take a look now how we represent a vector in a moving coordinate system in a inertial coordinate system which is stationary. So we have here a cylindrical robot where we have theta is the yaw, and z is going up and down, and y is going in and out. And you see over here that this is a truncated cylinder, and that's why we call it a cylindrical robot. Now, the point over here, this is a schematic diagram, and the tip of the gripper is represented by position vector r, and we can say that r is equal to r1, which is fixed in the rotating coordinate system. And then we have uv, it's a coordinate system which is rotating, and we have another vector r2 which is moving with respect to u and v. So r is equal r1 plus r2. Now if you want to take the absolute derivative of r, which is the absolute velocity of this point, we can derive these two vectors, and it will become dr1 dt plus dr2 dt. This is the absolute velocity of this point, and this is the absolute velocity of this point, r2, with respect to this point. Now, dr2 dt, this absolute velocity is equal to the relative velocity of r2 within coordinate system u and v, but on top of it we have to include the effect of the rotation of this vector r1 to which r2 is connected to, and that effect is omega, which is the velocity of the rotating coordinate system over here, theta dot, cos r2. So omega cos r2, if we do the cross product of the angular velocity cos r2, provide us the element of the velocity of the tip of r2 due to the angular velocity of the moving coordinate system, and to it we have to add the relative velocity within that moving coordinate system. This is a very basic elementary equation that we need to use in kinematics of robots. When we take the second derivative of r2, then again we derive dr1 dt and plus dr2 dt, and we come up with dr1 squared dt squared, and this square r2 dt squared. This is the absolute acceleration of this point plus the absolute acceleration of this point with respect to this point. And when we expand the absolute acceleration of this point with respect to this point, which is d squared r2 dt squared, then using the same rule as we had before, we first have to take omega and cross it with this whole expression of dr2 dt. So omega cross omega cos r2, and we also have to have plus r2 dot. So this whole expression over here is being crossed with omega, and then we have to take the relative velocity, which is omega dot cos r2 plus omega cos R2 dot plus R2 double dot. So this is the absolute acceleration of this point here with respect to this point in a moving coordinate, in the inertial coordinate system. So if we expand these terms, okay, we get d squared r2 dt squared, this is the absolute acceleration, equals omega cos r2 plus omega cos r2 dot plus omega dot r2 plus omega cos r dot 2 plus r2 double dot. Now when we combine terms, what we get is that omega cos r2, and we have omega dot, which is alpha cos r2, and then you see that we have omega cos r2 here and omega cos r2 here, and we combine them to 2 omega cos r2 dot plus r2 double dot. And then we combine, we get the final expression, which is very important, which says the following, that the absolute acceleration of this point on a robot with respect to this point, that may be a link of a robot, that may be a joint, that may be another joint. So the absolute acceleration of this joint with respect to this joint equals to the absolute acceleration of this joint, right in here, plus the omega cos r2, which is the centrifugal acceleration of this point with respect to this point, and it has a magnitude of omega times r2 dot, which is this vector, and has a direction into the center of rotation. And then it has a tangential acceleration alpha cos r2, and this is alpha is the angular acceleration of this moving element of the robot cos r2, and this is the tangential acceleration. So if alpha is in this direction, tangential acceleration will be in this direction. And then we have an expression 2 omega cos r2 dot, which is called the Coriolis acceleration, and it's a cross product of omega cos the relative velocity of R2. You see that over here, this point is moving with respect to this point while it's rotating, and this will be, that velocity will be R2 dot. And finally, if this point is accelerating in this moving coordinate system, it will be called R2 double dot, and this is the so-called relative acceleration within the moving coordinate system. So this is an extremely important expression in robot kinematics, where we can find the absolute acceleration of one point on a robot with respect to another non-robot, and we can follow up the entire robot links all the way to a point where we define the velocity and acceleration, and from it we can resolve the expressions for all the robot kinematics. We have here a few examples. We are not going to go through each one of them, but I recommend that you follow step by step the procedures. These are numerical values for the same problem over here, and then plugging in the values, you can see how we solve for the velocity and acceleration in the inertial coordinate system, and we can do it both graphically and analytically, and we have other presentations online that describe it in more details. Here's another example that shows the same process, as well as the process of finding the graphical solution to the absolute acceleration of the point of interest over here, which is the tool center point of the gripper. Here's another example where we have a robot with two links, and we are given the values of the angular position We also given the values of the link length and the angular acceleration and velocity, and we are solving both graphically and analytically the kinematic problem. In order to make or simplify the process of multiplying matrices and vectors and doing cross products, it is recommended that the students will download the MathCAD. It's free for life for certain operations, including matrix transformations, and we could define each one of these vectors as a one column matrix, and we can define, for example, depending which direction and what sign we have, including the units for each one of these vectors. It's important to realize that we do the cross product of omega cross a vector, then we always use radians per second for omega, not RPM or degrees per second. The values are with radians, and then MathCAD is doing all the unit and the transformation for us. And you can follow this procedure over here step by step, as well as the graphical solution, and see how the two correlate to each other. Looking at forward and backward kinematics, the definition of forward kinematics is the process where we are known the position of the links of the robot. Theta 1 is the position of this link with respect to this link, and theta 2 is the position of this link with respect to this link. Knowing these thetas, when we calculate the position of the end effector or tool center point in x, y, and z coordinate system, this is a forward kinematics from theta to x, y, z. Going backwards, knowing x, y, z, and finding theta 1, theta 2, theta 3 is called the inverse kinematics. This is the forward, this is the inverse. The forward kinematics is pretty straightforward, and the inverse kinematics is a more complex process to solve. We see, for example, over here an example of forward kinematics. To find out the position of the tool center point, we see that if we take L1 times cosine theta 1 plus L2 times cosine theta 2 plus theta 1, which is the angle between this link and the horizontal, and if we take then this length L3 times cosine theta 1 plus theta 2 plus theta 3, which is the angle of this link with respect to the horizontal, and we add all them together, we come up with the position of the tool center point in the x direction. X is equal to this expression. Straightforward. Similarly, we can find it for y, and we have expression over here for the theta. However, if we given x, y, z to find out what is theta 1, theta 2, theta 3, it's quite a complex process, and you see that the expression over here become quite involved. Typically, the process of solving inverse kinematic could be done graphically, pretty straightforward. If we are given, for example, a position of the tool center point, and we know this configuration, we can construct a circle where this link will be, and a circle from this center where the other link at the intersection are going to provide us the solution for the inverse kinematic, knowing this angle over here and knowing the position of the tip or the tool center point. There is also a numerical method where we could find the inverse kinematics, the thetas, knowing x using the Jacobian matrix. The Jacobian matrix is simply a matrix that takes the partial derivatives of the forward kinematics f with respect to the angular position, and when we take the inverse of the Jacobian and we multiply it times a small increment of x, we can find a small increment in theta, and we can actually integrate that and add a small theta to the previous theta, and this way solve the problem numerically. Other useful expressions for relationship between kinematic variables are given in this matrix. You could develop that in Excel spreadsheet, and what it says is that when we look at the motion profile, typical motion profile of a robot link, this is the y-axis represent the x, the velocity and acceleration, and over here the x represents the time. You see in red that this is the trapezoidal velocity profile, and it has a acceleration in this portion, constant velocity, and deceleration in this portion, and then it has a dwell in blue. We see the displacement. Now the relationship in this area between time, velocity, acceleration, and x is given with this formulation. Given any two, we can calculate the other two. For example, given a and v, we can calculate x and t. Given a and x, we can calculate v and t, and so forth and so forth. And then we could use this expression in order to develop, given, for example, a known displacement during a motion profile, and given time, we can calculate what should be the velocity and acceleration for that profile during the acceleration and deceleration. And of course, we can use simple algebraic relationship for the constant velocity. The kinematic specification of a robot, such as the scorebot, which we'll be using in a lab, are given to us in a catalog. We see over here that we have the weight, maximum payload, the n effector, and the gripper opening that are given to us in degrees and in millimeters. We see that we have the number of axes. Each axis has given a range of rotation, also has an effective speed. All of these are kinematic variables. We will be using them in a lab when we do some calculation. This is a summary of the motion range for each one of the robot axes. We have 5 axes plus servo gripper, and this is an articulating robot. We have also a set of 6 motors. Each motor has a given torque and also given power. We have here a mechanism where we talk about dynamics and transmission of actuators. We'll be using these gear ratios and the transmission, which we will investigate the way it's constructed within the robot, including timing belt gears and lead screw. And then we have also the specification of repeatability, maximum velocity in both millimeters per second and inches per second, and also the environmental condition of the robot. These are the definitions of the robot, and we will once again will be doing most of the experiments in a lab using this robot. This concludes our kinematic sections, and we will add to it additional YouTube presentations, both in kinematics as well as dynamics based for the exercises. Thank you.